Yeah, let me work an example for you.
You got this. You yesterday.
Yeah, you're the electrician for the entire week. So. Huh? Okay. First of all, let me show you something about the loop rule. Let's say that we just had a normal combination circuit like this. We haven't seen this explicitly, but you should know. If I have a circuit like this, how many currents are in this circuit, first of all? Not one, not two. There are 3 currents, right? There's a current here, I'll call this I1. Then there's another current here, I2, and another current here, I3. I1 is equal to the sum of I2 plus I3. Right, there are 3 distinct currents. Anytime you have a junction, like here and here, you're going to have a different current. Let's call this R1, I'll call this R2, and I'll call this R3. I'll just call this V. Now, I can write the loop rule for any closed loop. So for example, if I start here, and I go through this circuit, that's a closed loop, right? I began and finished at the same point. So if I were to write the loop rule beginning at this point and going in this direction, I would say V minus I1R1 minus I2R2 equals 0. That's a correct application of the loop rule. We don't need to do it that way because we do it a different way. It's easier just to find the equivalent resistance and then use Ohm's law to find the various currents and voltages. But you could do it this way. Did I do this already? No. Okay. I could do other equations just like we did before. Like, for example, I could do the junction rule right here. I could say I1 equals I2 plus I3. Right. I could do another loop. Instead of going across the top branch, I could go through the bottom branch like that. And that would be V minus I1R1 minus I3R3 equals 0. Those are all correct equations. And now I have 3 distinct equations that you could solve. Well, like I said, it's complicated to solve those, so why would you do that? To show you another loop, you could also do something like this. You could start here and go through like this. And that would be minus I2R2 plus I3R3 equals 0. So here, even though I haven't done like the big loop of the circuit, it's still a closed loop because I'm starting and finishing at the same point. Was it?
So you just went around the small square.
Right, I just started here and went around and got back here. It's still a loop. So the loop rule applies to any closed loop that you have. That's the point there. All right. All right, let's do another problem. Let's say that I have a multi-loop circuit. That one's pretty simple. It's 3 volts, 1 ohm, 2 ohms. It's pretty simple. Yours could be a little more complicated than that. Maybe an extra resistor thrown in there, an extra battery. But one thing that it will have is that it will have one branch of the circuit that doesn't have a resistor. So that makes the algebra a lot easier. First thing you want to do is just identify your currents. You have 3 distinct currents here. And so I want to label the directions for those currents. Doesn't matter the direction that you choose. So I'll choose this to be I1. I'll choose this to be I2. And then I'll choose this to be I3. Those are chosen randomly, just however you want to choose them. Just recognizing where those currents flow. And now I want to go through the circuit. I'm going to start here and do the left loop, and I'll get 2 is positive because it's ramping up, minus 2i2 equals 0. That's the left loop. I'm going to call this equation 1. Now, for the next loop, you could either do the big or the right loop. I'm going to do the right loop. I'll start here and go in this direction. 3 minus 2i3 minus i2. Oh, I made a mistake there, didn't I? It should be minus i2 equals 0. Let me fix this up here. This should just be minus i2. Did y'all catch that? Yeah. Anyway. All right, so 2 minus 1 i2 up there. That's for that left loop. Sorry for that. And then the third equation, you just use the junction rule. So pick any junction. I'll take the top one. Incomings are I1 and I3. I1 plus I3 equals I2. All right, and now I want to solve these. This is pretty simple to solve, right? The algebra is pretty simple. Because look, equation 1, I can solve outright and just say I2 equals 2 amps. Then I can take this and solve it for I3. This 2 is 1. I3 is equal to 1/2. Does that work out to... Yeah, that works out. 1/2 amp. And then I can solve here for I1, which is going to be I2 minus I3, which is going to be 3/2 amps. In this case, they all came out positive. If any one of them came out negative, so for example, let's say that this came out negative, then when you plugged it in over here, you'd plug it in as -2. We did some examples like that, but I just want to make sure that's clear. Jose? For which one? I was just doing my head. Let me just double check. So solving the second equation, I would say 3 minus 2i3 minus I2, which is minus 2, equals 0. So that's 1 minus 2i3 equals 0. 1 minus 2 times 1/2 is 0. Yeah, that's correct. All right. And then so those are our currents. As I said, if they came out negative, the direction would just be opposite. But I'll ask you to give the direction. Here for I2, it's down. That's as we labeled it. I3, you could either say up, or you could say that it's counterclockwise. And then I1, you could either say up, or you could say it's clockwise. Either way, it'd be fine. You want to do the matrix stuff too? Yeah, hold on. Rob? Okay. The bulk of your points are going to come from just writing the equation. So this should be like a perfect problem. You should have it perfectly. All right, just be careful with it. It's 20 points, so it's not insubstantial. Then you can pick up a few extra points here by doing this with that matrix method. First, I'm just going to rewrite each equation. And you don't have to go through all these steps, but you do need to get to the matrix. I would have 0 I1 minus 1 I2 plus 0 I3 equals -2. I'm just writing this equation 1. There are no I1 and I3 terms, so I just give zeros for each of them. I2 has a -1 coefficient, and then this 2 I take over here, so it becomes negative. What I've written here is I've said 0 I1 minus I2 plus 0 I3 equals -2. And this is the same equation as equation 1.
What is
I had 2 minus I2 equals 0. And so I say minus I2 equals -2. I take that constant over to the right side of the equation. And that becomes the augmented part of your matrix. This is called an augmented matrix. All right. The second equation.
Question.
Yeah, Andrew.
What if it was a positive I2?
Mm-hmm. Then it would be positive 1.
Be positive instead of negative for the fourth number?
If I2 right here was positive, no, this would still be negative.
Oh,
If you get it negative, you just take it over to the opposite side of the equation.
Okay, so I'm just curious now.
Okay. Are y'all going to try to do this on the exam? Is it worth the time?
You just break the constants up, and bring
Yeah.
all your constants over to, so they're all equal.
Mm-hmm. I think it's worth your time. I think the exam is fairly straightforward, so you'll probably have plenty of time to do this.
To work in the top way and then work in this way?
No, you don't have to do that.
Or we get a couple more points.
Yeah, if you don't have to do it by algebra, but you have to show me the steps on the matrix. I need to see your intermediate steps because I know you can put it in your calculator, and I'm okay with you checking your answer like that, but I need to see the intermediate steps. Okay, and you'll need to write the equations. Like I'll need to see the equations right now.
0, -1, -2.
Yeah, so here I get 0, -1, -2, -3. Those are the coefficients of I1, I2, and I3. I1 is not in this equation, so it gets a 0. I2 has -1, I3 has -2, and then this 3 right here goes over to the opposite side, so it becomes negative. And then over here I get 1, -1, 1, 0.
So you bring the I2 over and make the constant 0?
Right. Because you have to have it in the form of I1, I2, I3 for the matrix form. All right. So now I can do a couple of things. First, I can get rid of this -1 right here by subtracting row 1 from row 2. So I'm going to replace row 2 with row 2 minus row 1. And so that gives me 0 minus 0, -1 minus -1, which is 0, and -2 minus 0, which is 1, and then -3 minus -2, which is -3 plus 2, which is -1. I've just replaced row 2 with row 2 minus 1. Yeah, so I'm subtracting row 1 from row 2. I'm replacing row 2 with row 2 minus row 1. So here I have 0 minus 0, and that's equal to 0 right here. Here I have -1 minus -1, -1 plus 1, which is 0 right here. And then I have -2 minus 0, which is -2. And over here I get -3 minus -2, which is equal to -1, which is what I put right here. All right, and then 1, -1, 1, 0. You can do multiple steps, but I'm just going to do one step at a time. Actually, I'm going to do two steps here. I'm going to divide row 1 by -1. So I'm going to take row 1 and divide it by -1. I'm going to take row 3, or row 2 rather, and divide it by what? By -2. Because that makes that -2 in the I3 column into a 1.
So you can divide them by whatever to make.
Yeah, you can multiply them by a constant, which would be the same as dividing them by a constant. All right, so that gives me 0, 1, 0, 2. That's my I2 value, by the way, which is what I found up here was 2 amps. I2 is equal to 2. 0, 0, 1, 1/2. That should be the same as what I found for I3, which it is. And then 1, -1, 1, 0.
Why can't you do all this? Why can't you do all of this now too?
Why what?
Why can you do?
Oh, why can you? Well, have you ever in algebra, did you ever divide equations? Yeah, that's basically what we're doing. We're just dividing equations.
Yeah, see, I learned this system, it's the same system, but we left it in equation form,
Uh-huh.
and then you just brought the equations and you just brought it. So it's the same thing as a matrix, but you just left it in equation form.
Right. It's easier to work with matrices. You don't have all these variables floating around. And the real thing here is you want to be able to program this, and it's some easy algorithms to program this. And then you can extend it not just to a 3x3, but to, a million by a million set of equations, which is really useful. This isn't terribly useful because you're going to solve a set of equations. You're not going to do it this way. All right, so now we want to get rid of this -1 and this 1. So I'm going to replace row 3 with row 3 minus row 1, or no, plus row 1, excuse me. Replace row 3 with row 3 plus row 1. That's going to be 1 plus 0, -1 plus 1, which is 0, and 1 plus 0, and 0 plus 2. Now I'm going to replace row 3 with row 3 minus row 2. And that's going to be row 3 minus row 2. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 1 is 0. And 2 minus 1/2 is 3/2. That should be I1. Yeah, so 3/2. And now you can just reorder it. 1, 0, 0, 3/2. 0, 1, 0, 2. And 0, 0, 1, 1/2. And that's your final identity matrix, augmented identity matrix. So, if you have extra time on the test, you can go back and try
How
that.
do I correlate that with which one's I1?
Oh, okay, so this first column is our I1 column. So this is like 1 times I1 plus 0 times I2 plus 0 times I3 equals 3/2. So I1 equals 3/2. The second column is 0 times I1 plus 1 times I2 plus 0 times I3 equals 2. So I2 equals 2. That's true. What we found. And then this third column is 1 times I3 equals 1/2. So I3 equals 1/2. This is I1, as it's written here, I2, I3. All right. It's kind of fun. It's sort of like a little puzzle. Yeah.
Do you have to rearrange that like you did for the last one?
No, if you write it correctly, that's fine. Like if you write that, if the currents are correct, yeah. Like, can you leave it like this, you mean?
Yeah.
Yeah, that'd be fine, I guess, yeah. It doesn't look as nice, but...
So basically, like the objective is just to get the fourth numbers to be the amps.
No, the objective is to get nothing but 1, 1 in each row.
All right, so you just need a 1 in every row.
Right. This, a 1 in every row, and all others are zeros. This form right here is called an identity matrix, and the identity matrix is of this form. All right? That's your goal, is to get it in that form. And then, whatever you have here, here, and here are your answers in the augmented part.
Put 4x4, we'll just have the zeros, and there'll be 3 zeros and a 1.
Right, it'd be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1.
Too many zeros?
You know what I mean? It'd be just like that.
Yeah.
For
Yeah.
Okay?
That was the whole point.
All right. Any other questions?
Can we do another one where we're like writing equations, but one that's more complicated?
Yeah. And you will see some like that, like in the multiple choice, that are more complicated. I just won't make you solve the but these are, I mean, this is a test like question. This one right here,
I mean, I'm talking about the same level of difficulty.
this is the same level of difficulty.
Okay.
All right. When you solve that system of equations, I don't want to get bogged down in algebra because honestly, it takes me forever to try to track down, Because if you have more complicated than this, everybody's going to make a mistake. Nobody's going to get the right answer, and then there goes my day. All right. So I'd much rather have y'all just get it perfect. I can go down and say, oh, they have the right answer, and take just glance at it.
You make it quick, just make it all multiple choice.
Yeah, that sucks for y'all. Don't usually do as well on the multiple choice, unfortunately. Okay. What's that? All right. Like you could see something like this on the multiple choice part of the exam, where you have to pick out what is the correct equation. We did some examples like this in class. All right. In that case, I would give you the directions for the currents. So say, for example, I would give you this is I1, this is I2, and this is I3. And I would ask you to pick the correct or incorrect equations. Well, let's just practice writing the equations. So for the left loop, start wherever you want to start. How about we start right here and go in this direction? It's going to be what? Plus or minus? 4?
Plus.
All right, 4 minus 1I1. I'm going with the current. If I come up here and then start going down, plus 3 minus 2I2. That's all equal to 0 because I'll come back to where I started. All right. I can do the right loop as well. Let's just start right here and go down. That's going to be 3 minus 2I2. Got a second. Okay. What's the next term for the right loop? Minus 2I2. Minus 1I3. Right? Plus or minus 6? Plus 6 minus 2I3. And then that's equal to 0. And then you can do the big loop. Remember, you only need 3 equations, but we could do the big loop and then do the junction rule. Now let's say that we started right here. What is it going to be? 6 minus 2I3. What's next? Plus 1I1. That's coming up here. Here I'm going against the current, so it's positive. Minus 4. And my charges see a decrease in energy. Minus 1I3. That's equal to 0.
So if you want the junction rule, say starting from I2, it would be I1 plus I3.
Right. So if I write the junction rule up here, that's what you were saying? I1 and I3 are coming in. I2 is leaving. In equals I out. If you write it down here, it would be I2 equals I1 plus I3, which is the same thing. Does that help a little bit, Lauren? Yeah. You'll see a couple questions like that. I think I actually had 2 questions. Which of these is the correct equation? Just by mistake. I had 2 of something. I forget what it was. They weren't identical questions, but it's important. The loop rule is really powerful when you're looking at a complicated circuit because you can pick out any one individual loop. Like in that combination circuit where we just picked out that little loop in the circuit, you can pick out any loop and the loop rule is going to hold true. But I wouldn't make you solve something like this. Okay?
Can you go back to the right?
The right loop, right here? So I started right here for the right loop. I know I started right here because I see a positive 3 right here, and that means I have to be going in this direction across that 3-volt battery. 3 minus 2I2, I'm going with the current, so that's negative, minus 1I3, it's negative because I'm going with the current, plus 6, positive because I'm increasing in energy, minus 2I3 because I'm going with the current.
I got it. I just started at a different point.
Okay, that's fine. You should still have all the same terms in it.
Yeah.
You're welcome. What else, folks?
What?
Uh-huh.
Possible what it's RC.
Okay, you have some in your homework, but I mean, it's nothing complicated.
I think they're not that bad. I think there's one in 2008, the last one.
Yeah, they're usually pretty straightforward. 2008 exam 2.
Yeah.
Okay. So here I have a capacitor with initial potential difference of 100 volts. It's discharged through a resistor to equal 5 seconds. What is the time constant? Okay, let's just write down everything we have. So V naught equals 100 volts at t equal 5 seconds. Let me do a different one, okay? Is that okay? Nothing complicated on these, just sort of basic. What is the time constant? What is the charge kind of thing? Let's say that I have a circuit that looks like this. All right, it starts charging. I want to know, what is the time constant? Well, what is the time constant? What is it? It's 2 seconds, right? 1 megaohm is 2 microfarads. That's equal to 2 seconds. Notice micro and mega cancel out. And so how long does it take to fully charge this capacitor? Huh? Right, so 10 tau is equal to 20 seconds. So it's fully charged after 20 seconds. Likewise, if you were discharging the capacitor, it'd be fully discharged after 20 seconds.
So the current would be 0 after 20 seconds.
Right, because all the charge would be on the capacitor that could be on the capacitor, and so no more current would flow to it. All right, I could ask a couple different things. For example, what is Q? And I don't know, T equal 2 seconds, just to make the numbers easy. That would be Q naught times 1 minus e to the minus t over RC. Don't bother memorizing the equation, it'll be on your sheet. Q naught we can find to C times V. C is 2 microfarads, V was 10 volts, times 1 minus e to the minus 2 seconds, which is t, over my time constant, which is also 2 seconds, so that makes it easy. All right. So that's going to be 20 microcoulombs times whatever this is. If you're not familiar with the exponential function on your calculator, you should try to do that if you haven't yet. Yeah, it depends. Some of you have a caret. Sometimes you have like an e to the x button.
So we don't need that. You have that in scientific notation with the one's microfarad and then break it down to 10.
No, you can just express it in microcoulombs, and whatever your units are here and here, that'll be the units of your answer. Because this portion of the equation, it doesn't have any units. It's just a fraction. I get 0.63 for this thing right here. And then when I multiply that times 20, I get 12.6 microcoulombs. That's pretty basic, right? It's really just plugging in numbers. But you also need to know what that function looks like. And with this 1 minus e to the minus t over rc, this function looks like this. Or what does it look like? Oh, it's like this, where it asymptotes at Q, big Q, which is 20 microcoulombs. So I might ask you to just sketch something out. I could also ask you, like, as it's charging, what is the current? And we know the current actually decreases, so the current actually looks like this. It starts out at some maximum value of V over R, and then it decreases. So it's equal to I max times e to the minus t over RC, which will be V over R. That's 10 volts over 1 times 10 to the 6 ohms. Here I do have to convert it into SI units because you don't have a mega micro to cancel out. So it's e to the minus 2 over 2. 2 seconds over 2 seconds. And what's that? 1 times 10 to the minus 5 with e to the minus 1. That's 0.37. Alright, or express it however you like in decimal form. Alright, y'all feel comfortable with that? There's some homework problems similar. You should look at those. Look back at the old test. I think that's the test, really. Really straightforward. Combination circuits, too. Any other questions? We have a few more minutes if y'all want to do something else.
You just said like some multiple choice, like the grounding and the protective device, circuit breaker.
Mm-hmm. I think there's a free response actually about it too. Just sort of a short answer. Describe how this works or what this does. Jose? Whatever you want to do, I don't care. Yeah. All right.
Is it more like coulombs and stuff? Is that micro? Or
Micro.
like the little
Oh, right here? This symbol right here?
Mm-hmm.
Yeah, that's micro, 10 to the minus 6. It does sort of look like an M, doesn't it? I usually think it looks like a U, but it's not really. It looks more like an M than a U. Is it the U correspondence in the Greek alphabet? Right. Oh, okay.
It's just that when most people draw it, it's like.
Right. All right, folks. Anything else? All right. Should be a good exam. All right. I want good grades on it.
We all do.
I know you do. 7:15. I'll hand out the exam. If you wish to come in, you may.